Let's take a look at exponential equations and solving them one specific way, and that is using the exponential law. So today we're going to solve exponentials using the law of exponents. We're going to change the base if we need to, and we can even learn to check our solutions, which is always a good idea to make sure you get the problems right. So an exponential equation has a variable in the exponent. And you see a bunch later in this problem or in this video. You see one right here. You see how the variable is in the exponent here. That's what makes that an exponential equation. Now the exponent law says the following. If a to the x equals a to the, let's use a different letter, b, then x equals b. So if the bases are the same, then you can just set the exponents equal, right? You can throw away the bases in a way and just solve the little exponent equation here. So let's look at a couple of quick examples. You see how they're both tens? Well, we can just say, so 2x has to equal x plus 8, otherwise this won't work. I'm going to subtract 8 and I get x, or subtract x, and I get x equals 8. Now, how on earth would we check our answer? How would we check? Well, whenever you get a solution to an equation, you should always be able to just plug it back in. We're going to plug it in to check. Plug it in to check. So we get 10 to the 2 times 8. Does that equal 10 to the 8 plus 8 power? Well, sure enough, it does. 10 to the 16 equals 10 to the 16, and there you have the answer. So indeed, x equals 8 is the solution. So we don't need to check all of our answers all the time in this video at least, but that's how you do it. You plug that value in and make sure it works. Okay, now here the bases are some really scary fractions, right? No big deal. Since the bases are the same, you just set the exponents. I'm going to put the word so there just to drive home for your notes. So then we know that 5x plus 6 has to equal 2x. Now if I subtract 5x from both sides, I get 6 is equal to negative 3x. I divide by negative 3. I see my answer is x equals negative 2. X equals negative 2 is the solution to this exponential equation. Okay, so you're probably wondering, wait, but I bet all the bases in the world are not always the same. So that's right. Sometimes the bases are not the same. So we're going to do a little trickery to get them to be the same. Let's review a few rules. Recall the negative exponent rule. This is where you have x to the negative n power is the same thing as 1 over x to the nth. Okay, so for example, if I have 3 to the negative 4th power, that is not a negative number. If you type that in the calculator, and if you type 3 raised to the parenthesis negative 4 power, it's going to say that it's a fraction, 1 over 3 to the 4th. It's simply a tiny number. So negative exponents do not mean negative answers. They mean positive, tiny numbers. Okay, so we're going to use that rule here in a moment. And then the other exponent rule that you learned in Algebra 1, and I have a video that covers all the exponent rules if you need to search my channel and you can dig that out. But the power of a power rule says this. If you have x to the nth power, and then you raise it to the mth power, you multiply the exponents. It's n times m. For example, if you have 2 to the 3rd power, and then you square that, it's not 2 to the 6th, okay? This ends up being 2 to the, I'm sorry, it's not 2 to the 5th, it is 2 to the 6th. It's 2 to the 6th, and why? Why? Because what does it mean to square something? It's where you multiply it by itself 2 times. So that's 2 to the 3 plus 3 power, which is 6. But the shortcut is that you just multiply. So 3 times 2 is 6. 3 times 2 is 6. Okay, folks, we're going to use those to our advantage. So these are some examples where the bases are not the same. So let's look at 3 to the x equals 27. Is there a common base between the two? Can you convert one or both of them to a common base? It is 3. So we could say, note, a fact that we have here is that 3 to the third power is 27. So all of this stuff is what you would want to be thinking is, as I look at this question, is there a common base? So I'm going to rewrite it with the common base. So x equals 3 is the solution. And of course, you can plug it in here. If you plug in x equals 3, sure enough, 3 to the third power is 27. So that's where we converted them to the common base 3. All right, let's see what this next one has in store for us. Okay, so what about between 4 and 8? Is there a base, something to the something power, something to the something power, where they would have the same base? Well, 4 is 2 squared. 8 is 2 to the third power. Okay, so these are math facts that you have to realize and recognize. All right, so the x plus 3 is still the exponent. The 10x is still the exponent. See what I did here? I took this 4 and I turned it into 2 squared. I took this 8 and I turned it into 2 to the third power. And I put parentheses there because we need to think about our power of a power rule. What do we do when we have a power and a power? We just said a moment ago that we multiply. So this is the same thing as 2 to the 20x equals 2 to the 3 times the quantity x plus 3. Now let's keep solving, right? We'll come over here just to save a little room. 20x has to equal, and now let's just go ahead and do our distributive property, 3x plus 9. So if I subtract 3x on both sides, I get 17x equals 9. I divide by 17. I get a very bizarre answer, but it is the answer. X equals 9/17 is the solution to this exponential equation. This one right up here has the solution 9/17. Probably would never be able to guess and check that. Okay, maybe this first one, maybe you could have figured that one out without doing all the work, but this one was definitely more difficult. All right, let's see what we have over here. What is the common base between 8 and 16? What can we turn an 8 into? And then what could we turn a 16 into? Well, base 4 doesn't work, right? 4 squared is 16, but 4 to the first power is 4, not 8. So I think we're going to use 2 again. This is 2 to the third power, whereas the 16 is 2 to the fourth power. Now the exponents haven't changed yet here. So I write it like that. Okay, so now power of a power you multiply. So 2 to the 3 times the quantity x plus 1 has to equal 2 to the power of 4 times the quantity x minus 3. So we can come off to the side here and let's solve the equation. 3x plus 3 has to equal 4x minus 12. So if I subtract 3x on both sides, I get 3 equals x minus 12. I then add 12. So as it turns out, the number was quite large. X equals 15. And you can plug that in and test. Remember, you can always go back with your calculator or something and plug 15 in, and you should get the same answer on both sides of the equation. All right, I've got 3 more examples lined up here for you. And we've got a fraction. Remember what we set up above. Let me zoom out here and go back up here, because this always is something that students forget about, is that negative exponents do not mean negative answers. They mean numbers in the denominator. In other words, small numbers. So here we have a small number. It's 1/5. Okay, 1/5 is a small number. And I'm thinking the number 5, right? 5 is sort of a common base here because 5 squared is 25. So we can come over here with this 25 and rewrite it as 5 squared with the 6x still there. How could we rewrite this green 1/5 as a base 5? Well, it would be a negative exponent. It would be a negative exponent because that's what the rules say for fractions are actually negative exponents. So we can then keep solving. So negative x has to equal, and this would be 2 times 6x is 12x. All right, 12x. So if you add x on both sides, you get 0 equals 12x. If you divide by 12, we get an answer. It is x equals 0. The only time this statement is ever going to be true is if x equals 0. And you can plug that in. Remember, anything to the 0 power is 1. This gives me a chance to remind you that. Anything to the 0 power is 1. So remember that anything to the 0 power is 1. All right, I've got a similar example here. So you might want to pause the video and give this a try on your own, but let's look at this 1/9 and the 27. What would the common base be between those two? I think we could write them both as a base 3. Base 3. So what would the exponents be to make that happen? It would be 3 to the negative second over here, and it would be 3 to the third power over here. 3 to the third power is 27. Again, you're going to have to remember these math facts and how to work with exponents. Over here, this is x minus 1 up in the exponent. So now we have 9x, right? When you multiply these two, you get 9x. Now let's multiply these, and we get negative 2x plus 2. Negative 2x plus 2. So if I add 2x on both sides, I get 11x equals 2. If you divide by 11, I get x equals 2 11ths would be the answer here. X equals 2 11ths. And another very strange answer that I doubt you could just come up with out of thin air and guess and check. Okay, what about this one? Oh my goodness. The bases are very different, and if you think about it, there is no common base because 7 to the first is 7, 7 to the second is 49. We're already well past 30. So do you have any thoughts on this? 7 to the what power would ever be negative 30? I did a pause there purposely. 7 to the what power would ever be negative? No solution. No solution. Why? The right side is always positive. If you take 7 to the first power, 7 to the second power, 7 to the negative fifth power, it's all positive all the time. Remember, negative exponents don't make negative answers. So this answer is no solution, and it was because of the negative here. All right, the negative in the front doomed this problem from the beginning. There is no solution to this. All right, so let's dial back here. What did we learn today? We learned how to solve exponential equations using the law of exponents, right? And we had to change the base sometimes. And then we also learned how to check solutions. So not too bad, hopefully. You're probably wondering how would we solve something where there is no common base? And that's going to involve a logarithm, which is what we'll be working on the next couple sections. So we have to understand what a logarithm is first. And we're not there just yet. So today, we're just learning how to solve equations by changing the base and using that law of exponents. All right, good luck on your assignment, and until next time.